All right, well, good evening, grade 12s. And since you guys were like obviously 100% experts at doing the first homework assignment, I told you there'd be another one this week. So, 2 lessons should be keeping it under 3 hours. But yeah, you're going to find this one a little weird. Going to warn you ahead of time. The homework is a little weird. So please do it. And maybe we should have a help session at some point as well for this. But anyway, let's talk about this thing called electric fields. So exciting. I know you're going to love this. So look. See, what a field is, this concept of a field, okay, in physics. An electric field is just an area or a space that surrounds a charged particle or a charged object, okay? And that area, in that area, another charge will experience a force, okay? So that's the definition of a force field. It's just an area, okay, in which another object, if placed in that area, will experience a force because of the field that's present, like the electric field in this case. Now you can have gravitational fields, you can have magnetic fields. So there are different kinds of fields, force fields in physics. So today we're talking about electric fields. And the thing about electric fields is we have a choice to make. With gravity, we test gravitational fields with a mass. Okay, that makes sense because gravitational fields act on any object that has mass. Okay, but electric fields act on any object that have charge. Okay, so because there are two kinds of charge, we have to decide what kind of charge we use to test a field. Okay, so what I'm going to do is I'm just going to show you here what the convention is. These lines that surround this charged object, let's just focus on this one for a second. These lines that surround this charged object, okay, this positive charge in this case, that's the field surrounding a positively charged sphere, okay? Now, what I'm going to do is just using the color blue, I'm going to put a little dot in here. I'm going to call this Q, okay? Now, Q is a positive test charge. Okay, so the convention, and I'm just going to put this in the margin here, I'm just going to say note. By convention, fields or field arrows, okay, these arrows indicate the direction, okay, of force on a positive test charge, okay? So a positive test charge. So what we do is, like, I'm going to be holding a tiny little test charge in my hand, actually not so tiny, but anyway, a little test charge in my hand that by convention we always pick a positive charge to test with, okay? So that's why this green sphere here in the center is not the test charge. Let's say it's the Van de Graaff ball, like that thing that makes your hair stand up. Let's just pretend that's what that sphere represents. So this sphere is the charge that's generating the field, and you're testing it with charge Q. And if I put it right here where that dot is, then what happens is charge Q is going to experience a force right along that line. Now, if instead I put Q over here, my positive test charge, it's going to experience a force. It's going to be repelled, right, from that green positive charge that's producing the field. So it's going to be experiencing forces no matter where I put it. It's going to experience forces along these vector lines, okay? Now, of course, we could have drawn more lines, okay? So, for example, we could have a line. What if I put, some students say, what if you put the positive charge there? Well, I mean, obviously, it's just going to be repelled along a line. That was going to be a bit rough. Along a line, something like that, okay? So you can put more lines. The point is you have to make the diagram symmetrical because there is symmetry in the field all the way around, And so I can't have more lines on one side and less lines on the other. So really, my line spacing should be uniform, just to indicate that the field is pretty much uniform all the way around. So it's not like you experience a greater force if I put Q right here compared to if I put Q right here. It'll be the same size force. It'll be in a different direction though. So by spacing the lines out the same amount, what I'm trying to tell you in the picture is that the field is uniform all around. Okay. Now, what about negative charge? Well, if I take my little positive charge Q and place it right there, now remember, Q is always a positive test charge. Okay, it's a positive test charge. So by rule, it's a rule, we always test a field with a positive charge. So it's going to be attracted to that negative charge. Okay, so remember, there's kind of like, it's kind of weird. These arrows, we don't draw the test charge. We only draw, like, if you imagine this was, say, a planet of charge, like, because I know you could picture this with gravity. We could test Earth's gravitational field, and what we would do is dangle a little test mass, right? Say a 1 kilogram mass, and just dangle it around. We see it's always pointing down, okay? Well, a test charge, same thing. So Q is our little test charge that we're using to test this sphere that has a negative charge, and we're going to test the field all around it. And that field this time would look very much the same as this positive charge. The only difference is the negative charge will attract my test charge, and therefore all the arrows are pointing the other way. They're pointing towards the sphere instead of away from it. Okay. Otherwise, it's pretty much an identical shape of field. Okay. All right. What happens when you get two charges? Well, when you get two charges, let's say we put our test charge right here in the middle. Well, my test charge Q is going to be repelled from the positive charge and attracted to the negative charge. So it's actually going to experience a combined force towards the negative charge, right? And it's going to be strong in there. It's going to be at the same time being pushed away from the positive and pulled towards the negative. Okay. Now, if I were to put it, this is going to seem a little strange. If I were to put it here, what's happening is in that exact spot there, I'll use the color, maybe I can do this. I'll use the color green. It's going to be repelled, okay, from that green charge like that, but it's going to be attracted to the red one. But since the red one is much farther away, I'll see here if I have to draw a line straight to it. Okay, whoops, no, it's not very good. Here, let me fix that. Okay, so let me fix, I'll just draw my blue dot again because it's not cooperating very well. Okay, so here's my blue charge Q. Okay, it's a positive test charge. There's going to be a tiny little red force that's like that, and the reason why it's so small is because the green one's bigger because the green charge is closer. So it's attracted to the red one, repelled from the green one. Now if I add these vectors tip to tail, okay, if I move that one so it's tip to tail over there, I'll use, wow, this thing's being difficult. So, okay. It really doesn't want to work for me. Wow, that's different. Okay, so here's the deal. What's happening is this red vector, if I move it over there, we see that the net force is going to be along this line. So the net force is the combination of the green and the red vector. So the push from the green guy and then the pull from the red one on my test charge Q, which is a positive test charge. And I will get a line, I'll color it black, it's a little easier, like that, okay, along the field line indicated, right? So if I put my test charge here, the green force would be like on on a straight line away from this like that, but you see the red one will be on, I'll do my best to draw this, on a line like this towards that. Now if I combine these two things together, tip to tail, I will get the black line like that. So you see how these field diagrams work. Now you're not going to have to draw them the way I'm drawing it with my little test charge cue, but just to show you what these arrows mean. These arrows mean that if you put a test charge somewhere in the picture, the arrow will tell you, the line will tell you what direction the net force would be on that object. Okay, so we can see that if I put my test charge, and I'll go back to blue for the test charge, if I put my test charge right there, for example, if I put it right there, well, the force at that particular spot, right, if I zoom in, is in that direction, okay? Now if I put the test charge here, and that particular spot, it's in that direction. So these field lines indicate the direction of force on a positive test charge, okay? And that's it for field diagrams. You're only going to have to know these 4 diagrams for a quiz or a test or something like that. So what they look like. Usually I get students to draw them, but with this pandemic, I don't know if I'll be able to do that. But I'll find another way, okay, of asking you questions about that. I wanted to show you that these fields are symmetrical. Okay, they have symmetry in them because like the charges are equally sized. If you happen to have charges that are not equally sized, like here we have a positive charge Q and a negative charge which is 3 times bigger. Well, we see the negative one has a higher concentration of arrows around it. That's a way of showing that the field is stronger there. Okay, but yeah, this one does not have the symmetry in it that the other diagrams have because the charges are not symmetrical. They're not just Q and Q, right? Okay, this one, by the way, is called a dipole. Okay, and this is called a charge double. Okay, or a double charge sometimes it's called. Anyway, and these ones individually are called point charges. Okay, so that's how you draw diagrams. Unfortunately, the lesson does not end there. We have to talk about something else, and I'm going to start the note down here. I'm going to call this note electric field intensity. Okay. Now I'm gonna tell you this, that the electric field intensity is the same as the force per unit of test charge. Okay, and it is oh, pardon me. I think I lost you. No, I still have you. Okay, that's weird because my computer shut down. All right, so the force per unit of test charge. Yeah, okay, now I'm just going to say, just as a little note, 1 coulomb of charge. Oh, gosh. Pen, I'm starting to lose my pen tip here. 1 unit of charge. Sorry, pardon me. 1 coulomb of charge is extremely large. That's probably about 1,000,000 times larger than what you would get if you touched your hand on the static ball and your hair stood up. So, and that's a very strong field that you're feeling there, enough to give you like a pretty good jolt. Not going to hurt you or kill you or anything like that, or stop your heart because it's just a static electric charge. But times that by 1,000,000 and you're dead. Okay, so 1 coulomb of charge is like 1,000,000 times more than what you get on that Van de Graaff machine. That's like 1,000,000 Van de Graaff machines. You touch that and it all discharges at once at that voltage that it's at. It's going to kill you for sure. If there was a coulomb on that machine, you would never touch it. It would be extremely dangerous. It would never get that high though. It just can't do it. It's too much electric potential building up. Okay, it just discharges into the air when it gets more than about a microcoulomb of charge on it. All right, so anyway, this is the definition of field intensity. Now we use a Greek letter epsilon for field intensity, which looks like that. Okay, little vector on it. Okay, and epsilon is equal to the electric force, okay, which is also a vector. But you divide by Q, and Q is your test charge. Okay, so might as well call it Q1. Okay, because now there's Q1 and Q2. So we'll call Q1 the test charge, and Q2 is the charge that you're testing the field around. Okay, so now look, I'm gonna redo this a little bit. I'm just gonna say recall that the electric field between two charges is K, Q1, Q2, okay, divided by R squared. Well now, where K, by the way, is 9.0 times 10 to the 9 newtons times meters squared per coulomb squared, okay? Right, so that's your electric field constant. And the deal is, this is a force 2, okay? Or sorry, this is a vector 2. And then the electric field intensity is therefore going to equal this expression here divided by Q1. So it's Fe over Q1, that's by definition. Okay, where Q1 is your test charge, so that's going to divide out, and you end up just getting KQ2. Pardon me. Oh gosh, I gotta fix this eraser. It's terrible. KQ2 over R squared. Okay, so now this is a formula in your textbook. KQ2 over R squared. And what it's useful for is like determining the field intensity around some charge. And the charge that they give you in the problem is always Q2. Okay, the test charge is basically a 1 coulomb positive test charge. Okay, so you're going to get some unusual questions. So let me get to that right now. I'll give you some examples. Okay, and I'll just finish this lesson with some examples. Now it's going to take me a while to show you some of these things. Some of them are a little weird. You have to use component methods sometimes. It just depends on the question. And the numbers usually are quite large. Okay, so just be aware that getting large answers is kind of normal. Remember that a coulomb test charge, okay, is a very, very large charge. And so you get large amounts of force. Okay, now I'm just going to put a little note in here on units. Okay, the unit of electric force is newtons, but when you divide by charge, you're going to get, for epsilon here, the unit is newtons per coulomb, which makes sense. Newton is for force, but then you divide by the test charge, so it's newtons per coulomb. It's kind of like saying on Earth the gravitational field intensity is 9.8 newtons, right, per kilogram. Okay, if that's logical. So there's right now, if I had a 1 kilogram mass in my hand, I'd feel 9.8 newtons of gravity on it. If I had a 2 kilogram mass, I'd feel 19.6 newtons of gravity. But it's still, no matter if I have 1 or 2 or 3, 4 kilograms, it's still 9.8 newtons per kilogram. So you see how what intensity is? We're going to divide out that whatever mass that is in my hand, we'll call it M2, right, if I was testing gravity, or M1, and M2 would be Earth's mass, let's say, that I'm testing. It's gravitational field that surrounds it, right? All right, so anyway, with electric fields, it's always a little more weird than gravity for students for some reason, but let's just see if we can do this. So all we got to do now is some examples. And I warn you ahead of time, it's a bit weird, okay, these questions. So I'll start with an easy one though. Let's say I had a -3 microcoulomb charge, and I say, okay, what is the electric field intensity? 1.5 meters. Now this could be the charge on the Van de Graaff ball, right? -3 microcoulombs, probably like, it's probably around there. Most of the time we use it, okay? And so what is the electric field intensity at this point? We'll call it X, okay? So what is the electric field intensity right there? Now some students will say, well, what? There's nothing there. But you're wrong. See, what we're putting there is a test charge. Okay, but I don't have to tell you how much that test charge is because it divides out. We don't need it. Okay, so anyway, they'll just point to a point in space. They'll say, what's the field intensity right there? Well, you just go ahead and use a formula. Okay, so you would say the electric field intensity is KQ2 over R squared. Now that is Q2. It's not your test charge. Your Q1 is gone. Okay, we took it out and we're just saying, all right, per coulomb of Q1, per coulomb of test charge, how much force do you get? All right, we'll just plug these numbers in. So it'll be 9 times 10 to the 9, right? Times 3 microcoulombs. Remember, never put the sign in. Never put it in. Don't put a negative. Just put 3 times 10 to the negative 6. And then you're going to divide that by, this is R. So it's going to be 1.5 squared. Piece of cake, right? All right, I need to get the calculator out because all right, so let me do that. Okay. My wife took my calculator, so this is going to take me a second. 9 times 10 to the 9 times 3 times 10 to the negative 6 divided by 1.5 squared equals, I get 12,000. So it's a big number. 12,000 newtons per coulomb. Now here's the deal. Okay, when you're looking at this, what kind of charge are we going to put there? So I'm going to put this little blue dot. What kind of charge do we put there? Okay, well, we're going to put always the rule, it's a rule to put a positive charge. So this thing is experiencing a force because it's positive. That field has to be, sorry, I don't know why I wrote that, has to be in that direction. Let me switch back to a better pen. It has to be in that direction because if I put a positive charge there, it's going to be attracted to that negative charge Q2. Okay, so I'm going to put in brackets that this charge has to be, the force, I'm sorry, has to be to the left. Okay, the electric field intensity. And 12,000 newtons per coulomb. Now, if you're worried that that's a huge number, well, remember, if you brought a coulomb of test charge, that's like bringing a lightning bolt to the party here. Okay, so the force would be huge if you could contain the charge in that lightning bolt into a sphere or something and place it there. Yeah, well, maybe you just got a weak Van der Graaf machine with just 3/millionths of a coulomb. But that 1 coulomb you brought to the party here is extraordinarily dangerous and will experience a tremendously large force. Okay, so 12,000 newtons per coulomb to the left. How do we get the direction? Because we know it had to be attracted to the positive charge, and so, or to the negative charge. Positive, negative attract, right? We always test with a positive charge, so that's it. Okay, so there's example number 1. Just a point charge, very simple. Example number 2. What happens if we have more than one charge? Okay, so let's do this. Let's keep our little 3 microcoulombs. That guy, he's not going anywhere. So there's our -3 microcoulombs. Now I'm going to put a positive 6 microcoulombs here. I'm going to put 2 charges in the picture. Sorry, my pen is almost broken. Positive 6 microcoulombs here. I'm going to say these 2 charges are 2.5 meters apart, but that's not the end of the story. I'm going to ask you, at a distance of 1 meter here, I'm going to ask you, put a little point here, let's call it point X again. My question for you is, what is the net field intensity equal to at point X? at this where this black dot is. Okay, actually I'll put the point X right on it. Okay, what is the field intensity at point X? Now, if you want, you can draw a little free body diagram of this, and I'm going to do it right on the spot. So I'm going to draw my little blue box. I'm going to put a positive test charge there. Now, a positive test charge will be attracted, so that's this force of attraction. It's going to be attracted to that guy. Let's call that E1. Okay, because positive and negative attract, but it's going to be repelled, and I'll use a red one. It's going to be repelled by this guy. So it's going to go like that. That's E2. Okay, now I'm going to continue this line here. We're going to need to know what theta is, and theta down here. It's the same angle. They're opposite angles, so they're the same. And this is a two-dimensional problem. So everyone's favorite, this is a component method thing, and you're going to have to use component method for this. Okay, there are two vectors in this thing that we're trying to add. Now first, let's get the magnitude of these vectors, okay, before we can use the component method. So for that, we use a formula. So what is E1 equal to? Well, E1 would equal K Q1 over R1 squared. Now, I'm calling, in this case, I know it's easy to get confused. I'm calling this one Q1, calling that one Q2. Okay, I can call it Q10 if I wanted to. It's totally random that I'm calling them what I'm calling them. Okay, you're gonna bug me and say, oh, but he canceled out Q1 in the formula. Q is just the charge you're testing. In this case, it's that -3 microcoulombs. Okay, so now I'm gonna plug the numbers in, and you get 9 times 10 to the 9 times -3 times 10 to the -6. So that's Q1, right? And then R1 is this distance. So it's divided by 1 squared. Now taking my calculator, 9, what is it? 9, I'm not used to this calculator. 9 exponent 9 times, oops, I broke a rule. Don't put the negative sign in there. Okay,